audio, so you need to not talk bad about anybody. No political comments.
Oh,
Because you got no political comments.
we are recording?
Yeah, we're just recording what's on the screen and what we say. That mic will pick up everything in the room. Trust me, I've used those before. It will pick up everything in the room. Okay, so let's go through this and see if we can get this. Oh, should have picked up the phone. That's what I did wrong. Take that off. Here we go.
A series parallel or combination circuit is shown here. Contains elements of both series and parallel circuits. Components that are connected in series display the characteristics of a series circuit, while components connected in parallel display the characteristics of a parallel circuit.
Okay, so now we're moving into combinations. We're doing both. All right. So you guys, you seen that video with the advertisement for the new online shopping where the people have their little heads and they explode?
Oh,
Okay, and they got purple stuff coming out.
Jet.
Jet, yeah, the jet commercial, the heads explode. So let's not have that happen in here. So, okay, so here we have parallel components. Let's go on. Notice that this section here, R1, is in series, R5 is in series, and the rest is parallel. All right.
Two important points to remember about the characteristics of series parallel circuits are: components that are connected in series have the same current flowing through them, and components that are connected in parallel have the same voltage across them. These 2 points will be very helpful in understanding the operation of a series parallel or combination circuit.
Okay, let's go on to the next one. We'll actually begin to solve these.
Describe a method for identifying the series and parallel sections of a circuit. The series and parallel sections of a combination circuit can be identified by tracing the current path to find nodes that split the current and nodes that recombine the current. In the example, there are no nodes between the power supply and R1. Therefore, R1 is in series with the power supply, and all of the current from the power supply flows through R1.
Garrett, we're recording our audio in here. It's going to YouTube. Some other people. So you know what you say is getting recorded. So we're just recording the screen though. All right. Okay, so here we have a combination circuit, and notice our current. Our current in this portion here is in series. Okay, and it comes over here, and then we come over here and we split just like a parallel circuit. So what's constant in a series circuit? Current. So at this point, whatever's coming through here is going to be IT. That's a total current, okay? Because that's coming through here. And at this point, it's still going to be IT, right?
Yeah.
What are we going to come over here? What's going to happen here?
It's going to break off.
It's going to break off. And so now I is going to split in half. And it's coming down here, and it's coming down here.
Would it be the same? Would it still be IT at the bottom? Or
Yes.
they'll join back together?
They'll join back together. That makes sense?
Yes.
Basically, the electrons, all the electrons at this point here, try this again. All the electrons flowing through this circuit at this point, we're going to do red electron. They're all coming through here. All my electrons. And then when they get here, guess what? Now, depending on this resistor value, we're going to put a kink in the hose, right? We're going to choke it off. And so we're still going to have the same amount of electrons, but they're going to split off. And when they come back here, they're going to join together. And all the electrons are coming through there. Clear as mud. All right.
Mm-hmm.
Okay, let's move on to the next one.
When the current reaches the node where R2 and R3 are located, it splits between them. This means that R2 and R3 are in parallel. The current in a parallel section must recombine at some point. So you should trace the two lines to find the node where they recombine. In this case, it is easy to see where the currents recombine.
And that's what we just talked about.
You can also represent the components are in parallel as R2 double bar R3. The two vertical lines, or double bar, mean these two resistors are in parallel with each other. Being able to identify which components are in series and which are in parallel is very important when designing or troubleshooting a combination circuit. It should always be your first step in analyzing a combination circuit. Trace the current path to determine whether resistors R2 and R3 are in series or parallel configuration.
Okay. I don't want that up there. Okay, so we're coming through here, and they want to know is R3 and R2, are they in series or parallel with one another? Parallel.
Trace the current path to determine whether resistors R6 and R7 are in series or parallel configuration.
Okay, so we're going to move down here. Are R6 and R7, what are they in relation to one another? That's a key word there, in relation to one another.
Series? Parallel?
They are still in parallel.
Okay.
However, let's back up. We'll go ahead and answer that. But what is the relationship to R6 and R8? R6 and R8. Series. If it's back here, it's always going to be series. What's the relationship between R4 and R8? Series. Okay. So here we have parallel. All right.
It doesn't have to have the nodes.
I guess I don't understand the question.
Well, it said earlier, it said on the diagram, when it shows the nodes,
Oh,
in between those is the parallel.
yeah. Well, what they're saying here, that was just to show you where the current joins together. So here, inside of here, between these two nodes is parallel configuration. Between this node here is a series configuration. Here it splits. They didn't put a node there. Now we're in parallel configuration here. This is parallel, but we are still in parallel with R7 and R5. That makes sense? Because in actuality, the answer, if you want to be really technical, they didn't really ask that, but it would have said, what is the relationship between R7/R5 and R6? Parallel. But there's still parallel combinations. So let's go on to the next one.
Trace the current path to determine whether resistors R5 and R7 are in series or parallel configuration.
Series.
Series. So here comes the current, and it's going to split, but we don't care about that because they're only asking about this one. So everything's being forced through here. Here we have two kinks in the hose. Two kinks in the hose. It is series. All right.
Trace the current path in a combination circuit. In this procedure, you will determine which components are in series and which are in parallel in a combination circuit by tracing the current path through the circuit.
All right.
Please click on the pencil and paper to view the step-by-step instructions for performing this procedure.
We're going to do this. You probably have it Let's see, I think I handed that out. Let's see. Come on, pencil and paper.
Go for it.
That's going to require a mouse. Oh, it did open. It just opened it in another browser window. I have like 20 of them open now. So this is skill 1, and I believe this is also skill 1 on the document I handed you, correct?
You're right.
So you have it on your sheet that we can work through, so. So basically what they're wanting you to do is begin to trace the current. So the current's going to come through here, right? I guess I'm not allowed to draw on Adobe documents. Here, this is up here. Well, it's not letting me do this, but if we follow the path, we'll see that it comes through R1, and R1 is what with the entire circuit?
Series.
It is series. We'll try this again. Really know I'm not getting any. It's not working. So R1 is in series. What about R2?
Parallel.
Parallel. This is R2 right here. It's a little blurry, but that's R2. What about R3?
Parallel.
It's in parallel. And R4? Series. All right. Let's see what else it has. Here's another example down here. And I think here's your skill. I can draw on this one. Just download that one. All right, so we're on this one, skill 3. So examine figure 1-2 and determine which loads are in series and which loads are in parallel with the other loads. All right, so R1 in this example, see if I can draw. Yay, I can draw now. So R1 is what we're on now.
I don't think we have reasons.
Did I not put those up? That's okay. We'll just look on the board. That's fine. I think I cut that out of that lab, so that's fine. So we're going to look at this one. So R1 is in what with the rest of the circuit?
Series.
It's in series. All right. So R2 is right here. little blurry, but here's R2. What is that?
Parallel.
Parallel. Now it's asking for R3, parallel as well, all right? And R4 is parallel. And what about R5, which is down here? This is R5. It is series, all right? Would you say that R1 and R5 are in parallel? R1 and R5, are they in parallel?
No.
I'm so proud of you. No, they're not. Because follow the current. Just, take your finger and trace it out. It's coming through here. All right. And it can split or whatever, but in the end, all of the current will join back together at this point right here, which means that if I was going to look at it, I might as well just ignore all of this, rest of the circuit, and simply do this, which is the same as this. It's kind of tricky. That's the problem with a lot of these in your book, is they're tricky. They look a little different. All right. They'll try to trick you with how they do it. So let me scroll down on that one. What else we got? All right, so we have another question 4. What is R1? Which is right here. This is R1. R1 is what series or parallel? Parallel. It's in parallel configuration. R2 is in what? Right here. R2. It's parallel as well. And then R3 is down here, which is series configuration. They did that because they wanted to show you that it doesn't really matter if it goes in front of the parallel configuration, behind, etc., etc. Now, when we solve these, here's your hint. Here's your hint. Your voltages, Kirchhoff's law still applies. So the total voltage drops when they're in series, and the total current that's used when they're in parallel will still add up to be IT and ET, or voltage total. You with me? And current total.
So,
all right.
What again?
Kirchhoff, when you're doing these problems, there's going to be more than double, triple, quadruple places that if you mess up one calculation, the rest of it is wrong.
Mm-hmm.
So in order to check yourself, you can use Kirchhoff's law to add up the voltage drops, and then the current consumed across each resistor should equal the current total and the voltage total. Pretty much they're always going to give you one or the other. So you can add them up and make sure that it equals the source voltage or current, and make sure that that adds up so you know you did your math right.
List the 7 steps for solving a combination circuit. Solving a circuit involves determining unknown values of resistance, current, or voltage in a combination circuit. The 7 general steps for solving a circuit are: simplify the circuit, use R sub EQ, calculate total current, calculate the voltage drop, calculate branch currents, calculate the voltage of parallel resistances, make a summary. You may have to alter the order of the steps sometimes, depending on the information that you're given for the circuit. But in most cases, these 7 steps should help you find the information you need to know about the circuit.
Okay, so now it wants us to click on each one of these.
Simplify the circuit to a series circuit by finding the effective equivalent resistance, or R sub EQ, of each parallel section of the circuit.
So designation REQ right here is now going to stand in for like a R total of part of the circuit. Are you with me? We're going to have to solve the circuit. We're going to simplify it. So if we solve for the parallel portion of our combination circuit, we'll call that REQ equivalent for that little portion.
Use R sub EQ to calculate the total resistance, or R sub T, of the circuit by adding them to the series resistances.
Are you with me there? You're simply going to do, how do we calculate resistance in series? Add them up. All right, so we're going to use that REQ as a stand-in and simply add it to the rest of the circuits.
Calculate total current, or I sub T, using R sub T, or Ohm's law. Calculate the voltage drop across any series resistance or equivalent resistance you need to know using Ohm's law. Calculate the branch currents in a parallel section using the voltage drop across R sub EQ and Ohm's law. Use the branch currents and resistance values to calculate the voltage of the parallel resistances.
All right.
The following example will display how to use the 7-step process to solve a combination circuit. First, click on the resistor values of R sub 3 and R sub 4 to calculate their equivalent resistance.
Okay, so now we're going to begin to simplify this circuit. All right. And when we do that, first thing we want to do is we want to simplify R3 and R4. So what are we going to do? Add them.
Click on the resistance values of R sub 2 and R sub 3, 4 to calculate their equivalent resistance.
All right. So here, over here, pay attention. This is our original circuit. Here we're going to simplify it out. Okay, so let's see R2 and R34. Let's click here, because now we have this parallel. And how do we solve in parallel? What method?
Inverse.
The reciprocal method? All right, so.
Now the circuit is a simple series circuit. Click on the resistance values of R sub 1, R sub 2, 3, 4, and R sub 5 to calculate their equivalent resistance.
All right, so what is RT now?
200.
200 ohms. We're going to add that one, and that one.
Since R sub 1, R sub 2, 3, 4, and R sub 5 are in series, use the series resistance formula to determine their equivalent resistance. The equivalent resistance of the entire circuit is 200 ohms. Click on that value to replace R sub 1, R sub 2, 3, 4, and R sub 5 with one resistor that represents their equivalent resistance.
Okay, and so, what are they?
Click on 200.
I think they are, that's right. I want 200.
Now that the circuit has been reduced to a single load, the total or main line current can be calculated.
What
Click on the resistance
formula are we going to
R
use to
sub
calculate
T
current?
and the source voltage to calculate the total current.
Yeah, amps.
E over R.
E divided by R equals I. See which one they work out. Resistance value of RT. There we go. And we're going to use voltage.
Use Ohm's law to determine that the total current of the circuit is 120 milliamps. Click on that value to place it on the schematic.
Yeah, come on.
Now that the main line current is known, Begin determining the characteristics of individual components in the circuit. Click on the equivalent resistor R sub T to split it back to the 3 resistors that it represents.
So we went all the way to the front, now we're going to go all the way to the back. Now we're going to...
Since loads in series all have the same current, the main line current is also the current through R sub 1, R sub 2, 3, 4, and R sub 5. Click on the main line current, I sub T, to assign that value to the series resistors.
Okay, so they're saying that we have, what was it, 0.12 amps? So at this point here, I got 0.12 amps. This point here, I've got 0.12 amps. All right. Here I have 0.12 amps. Here it gets split, but it comes back together here and I have 0.12 amps. And here is 0.12 amps, and as well as here. Everybody understand how it's going?
Mm-hmm.
So we're coming through there. It only gets split in the parallel portion.
Yes, sir.
Now that the resistance and current through R sub 1 is known, Ohm's law can be used to calculate the voltage drop across R sub 1. Click on the values for R sub 1 and I sub R1 to calculate V sub R1.
Okay, so they want to know the voltage drop across resistor 1. What formula are we going to use?
I times R.
I times R. So E, or voltage, of R1 equals I, what, T? Because that's the same, all the way across, times R1, which would be, if it has a calculator.
Hold on here. 50 times 12. Let me get up the calculator.
Probably 0.2 there.
What is that? $50 times 0.12. 6.
To solve for V sub R1, substitute the current through R sub 1 and the resistance value of R sub 1 into Ohm's law and solve for voltage. 6 volts is the voltage drop across R sub 1. Click on the value to place it into the schematic. The voltage drop across R sub 5 can be determined the same way as R sub 1.
12.
Click on the values for R sub 5 and I sub R5 to calculate V sub R5.
Real quick, what's my voltage drop here and here?
3.
No, there's not one, because that's a parallel circuit. That was a trick question.
Oh.
Be prepared for that on the test.
Yeah.
I got you. There's no, that's where the current splits. The voltage at this point and this point, and at this point and this point will be, well, there'll be a voltage drop here. So it would be the same. Actually, the voltage here at these 2 dots here. Yeah, you probably get a voltage drop here, but well, anyway, that's the voltage here and here would be the same.
So the voltage would drop between R3 and R4?
Yes, it would.
Oh,
Yeah. So R3, between R3 and R4 would be another voltage drop.
yeah.
Which would all add up to be what?
6.
No. Would be VT, which is 24 volts.
Oh, I thought you meant like those.
It's all going to add up. If it doesn't add up, then you didn't do it right.
Oh, yeah, because that would
So,
add.
What do they want now? Click on R5 and IR5.
Gosh,
Okay, they're wanting to simplify over here. So there we go. Well, did I break it? Click on the values, of R5 and IR5 to calculate VR5.
Do you have that one thing clicked?
Maybe not.
To solve for V sub R5, substitute I sub R5, the current through R sub 5, and the resistance value of R sub 5 into Ohm's law and solve for voltage. 12 volts is the voltage drop across R sub 5. Click on the value to place it into the schematic.
No, so we would just know automatically that one drops 12 because it has to be 24, then that parallel, doesn't it?
Well, at this point, what do we know? What do we know? We know that we're dropping 6 volts here, right?
Mm-hmm.
And we know that we're dropping 12 volts here.
Mm-hmm.
So what is 12 plus 6?
18.
It's 18 volts. So what is 24 minus 18 volts?
6.
6. All right.
So
So we know that here is going to be 6 volts, because that's all that's left.
Mhm.
But that's split between that other configuration with all the other resistors.
Mhm.
But when it's simplified, we know, so basically we know, let's see if it pulls it up here in a second.
The voltage drop across the equivalent resistor R sub 2, 3, 4 is easy to determine since all the other voltages are known. Click on V sub T, V sub R1, and V sub R5 to determine V sub R2, 3, 4.
Basically, if we dropped, what did we say? We dropped 6 volts here,
Mhm.
and we dropped 12 volts here, and that left 6 volts left. That between here and here, with my meter, I would measure 6 volts. You with me? But there'll be, inside there will be some more voltage drops. So you see what happens if you mess up one calculation? You mess it all. So click on VT. Is it one? VT VR1 and VR5. Not to go, oh,
Yeah.
yeah, go here with the mouse.
Oh, it's better too.
Uh-huh. Click on VT.
The sum of all the voltage drops in the circuit must equal the source voltage.
That's what we just
V sub
discussed.
R2, 3, 4, the voltage drop across R sub 2, 3, 4 is 6 volts. Click on the value to place it into the schematic.
All right. There we
Now
go.
that V sub R2, 3, 4, the voltage drop across R sub 2, 3, 4 is known, begin determining the characteristics of the individual components within that parallel section. Click on the equivalent resistor R sub 2, 3, 4 to split it back into the 2 resistors it represents.
Okay. Now we're going to split it back. Well, somebody's head's cracking over there. I see it. I'm messing with it. If their head's cracking. Here we go. We're going to split it up. There we
This is the
go.
voltage reading across the parallel branch. This is the voltage drop across that branch. Since the voltage across each branch in a parallel circuit is the same, V sub R2 and V sub R34 are both 6 volts. Click
what I
on the
showed
voltage
you
reading of
earlier,
6
right?
volts to assign it to V sub R2 and V sub R34. Now Ohm's law can be used to calculate the current through each branch. Click on R sub 2 and V sub R2 to calculate I sub R2, the current through R sub 2.
Okay, so how are we going to calculate current? What formula we want to use? All right, so we're going to use
E divided by R.
E divided by R equals I. I of what? I across R2 is going to be solved with the voltage across, or the ohms of R2, and then we're going to have to use our voltage of VREQ equivalent. All right, let's try this again. Click on R2 and VR2.
To solve for I sub R2, the current through R sub 2, substitute V sub R2, the voltage drop across R sub 2, and the resistance value R sub 2 into Ohm's law and solve for current. 60 milliamps is the current through R sub 2. Click on the value to place it into the schematic.
So we have 6 volts, right? You see the 6 volts and 100 ohms right there? Let's put that in the schematic.
Now that the main line current, or I sub t, and the current for one branch of the parallel section is known, Kirchhoff's current law for parallel circuits can be used to calculate the current of the other branch in the parallel section. Click on I sub t and I sub R2 to calculate
Everybody
I
stand
sub
up.
R3,
Stand up.
4, the current through
Stand
R
up.
sub 3, 4.
Stretch. We're almost through.
I wish I could raise both arms.
Let's go turn. So it wants to do, click on IT and IR2 to calculate the next one. All right, so it wants you to click on, where's IT? Boy, there's a lot going on here. Here's IT, and let's click on IR2. Now, what do we know here at this point? If we're pulling, our total is 0.12 amps, and we're pulling 0.6 over here, then what do we got left over on the other side? 0.06 on the other side. So click on IT and IR2. There.
To solve for I sub R3, 4, the current through R sub 3.
So using Kirchhoff's law, we subtract the total
I sub t
from the current
through R
IR2, which gives
I
us
sub R2 into Kirchhoff's current law.
0.12 volts minus 0.6 volts, which gives us.
60 milliamps is the current through R sub 3, 4.
So that means
Value to
at this
insert
point
into the
here,
graphic.
we have that, because that's all that's left using Kirchhoff's law. You guys can sit down now. We're almost done. We'll take a break. We're not doing lab. We'll save the lab for tomorrow, but we're going to get through this. Because I think this actually, did you guys, anybody look at chapter 6 yet?
No.
Okay.
I haven't looked at it either.
Was there homework yesterday to read chapter 6?
If you had time after the test, but yeah, that's going to be your homework. I'm going to put it, it's already probably posted on Google Drive, so. So let's go ahead and put this in here. We're almost
Now
done.
that I sub R3, 4 is known, begin determining the characteristics of the individual components within the series branch of the parallel circuit.
So
Click on the equivalent
now
resistor
we're going to go
R sub
down and we're going to
to
determine
split
that
into the resistors it represents.
using what? What values we're going to use to determine that? Well, we're going to use IR3, 4, because that's what's going across that individual branch. And we know what our voltage is at that point. And so we're going to have to use VR2. It's going to be 6 volts. So it's going to be 6 volts at that point. So let's go on and place this in there.
Now that the current through R sub 3 and R sub 4 are known, the voltage drops across R sub 3 and R sub 4 can be found. Click on I sub R3, 4 to assign it to R sub 3 and R sub 4. Now that the current through R sub 3 and the resistance of R sub 3 are known, the voltage drop across R sub 3 can be calculated. Click on the values for the resistance of R sub 3 and the current through R sub 3, I sub R3 to calculate V sub R3, the voltage drop across R sub 3.
Oh, maybe I should just turn the audio on. Here we go. Now we're using Ohm's law.
R sub 3.
We're using Ohm's law, and we're calculating the voltage drop across this one resistor, which comes to 1.5 volts. All right, and we're going to put that 1.5 volts in there. And here we are going to calculate R4. So we want R4, and we want the current across R4, which it's a series circuit, so it's going to be the same value as 0.06. And we come up with a 4.5 voltage drop. Okay. Now, what do we notice about these values? This is where you do your double check on these calculations. 6 volts. All right. 6 volts. 1.5 volts. 12 volts. And 4.5 volts. So, what does that add up to? What is 6 plus 6 plus 1.5 plus 4.5 plus 12?
24.
24 volts using Kirchhoff's law, which tells me that the calculations were done correct. If those don't add up, you start over. Or backtrack.
Wait,
That's not
that's
right.
more than 24.
You shouldn't have
That's
those 6
that's
and everything.
30.
Did I miss one?
It should be 6 plus 1.5 plus 4.5 plus 12. You put one too many 6s.
Oh, yes. Thank you. Sorry. But my original circles were correct.
Yes.
Yes, my circles were correct. All right. Now that we've got that taken care of, let's see what else we have. The next one, I think we're almost to the lab, but we're going to stop at that point.
All in all.
Oh, now we have a little online practice. So, I tell you what, you're already logged on, you went through this. I want you to go through the online practice for the remainder of the class, and I'm going to stop the recording.